Right, let's tidy all this stuff away and take a look inside the Smart Active Balancer. So this comes with this Bluetooth dongle, and it's plugged into the UART stroke BT socket. And I've got to get this plug out, otherwise I don't think I can take this apart. Oh, I might be able to, but anyway, I'll take the plug out anyway. But it's quite tricky and I don't want to pull on these wires. There was a strain relief bit of heat shrink on this, but I think it was doing more harm than good, because it was kind of trapping these wires right at the top there, and then any bend or twist on here was amplified up at this point. So I took the heat shrink off. But let's try and pull this out with these chip pullers. Yeah, they work quite well. Okay, so let's get the box open. Four very similar, in fact I would venture to say the same size screws on this one. Okay, let's take a look inside, and things are very different inside here to the little capacitor active balancer. Let's get in a bit closer. Okay, this device is quite complex. I don't intend to give a full explanation of how this works, well, because I don't really know how it works, but we can look at some of the major elements. So inductor here, big tall thing, 2 ferrites stacked on top of each other, couple of capacitors, very different. This is 47 microfarads 100 volt. This is 470 microfarads 16 volts. Now there's some sort of inductor here, there's a little inductor down here, 47 microhenries. There are these two things, TR73. What are these? Are they transformers? They look like they might be transformers. And there's an absolute mass of components on here, including, what are these? Are these MOSFETs? I don't know. Would you have all these resistors on the arms of these MOSFETs? We'll have to have a closer look at those. Big single chip device here. It says on it Giga device, and it also says ARM, so it's an ARM Cortex CPU or system on a chip would be my guess. A little oscillator there. There are a few of these things which look like, the package looks like opto-isolators. I mean, are they opto-isolators? I don't actually know. And then there are a whole series of these switches. On here, they've only populated 3 of them because this is a 4S. Well, that's interesting. Why 3? I would have thought there'd be 4, because that is actually a 5-way connector. And on the back, there are more circuits here, only 2 of them. Oh, I wonder if that means that there are actually 5, 3 on the top side, 2 on the bottom side. They do look very similar, but that's a lot of switching, more switching, and masses more electronics here. There's a lot going on in here. I'll take a look at some of these chips, if any of them are identifiable. Right, a couple of things. This is a 24C, I think it was a 512, quite a large serial E2 PROM for holding parameter data. I'm surprised there isn't enough permanent storage in the main SoC for that, but yeah, there's that chip. This says HC595, so is that an octal latch, possibly for latching in output driver data for all of these channels of switches? And there can be a lot of those if you get the 16S version of this. This is a 4052, and I'm just wondering whether it's an old school CMOS 4052, whatever that is. Let's look it up. Yeah, CMOS multiplexer, demultiplexer. This is an EG27324, which is actually a motor driver. It's near the inductor, so I guess it's driving the inductor and capacitors using a motor driver. That's really quite interesting. More of these 4-pin devices over here, which look like opto-isolators. They may be opto-isolators. Now, what are these devices here with all these resistors, one on each leg? Well, these are CA-IS372X high-speed dual-channel digital isolators, designed for isolating digital from analog, I think, for noise immunity and stuff like that. Someone's had an absolute field day designing this thing. Oh, look, of course, yeah, this HC595 latch, you can put more of them on here in order to drive these other channels. So yeah, that is to latch digital data to switch all of these channels, I suppose, to decide which pair of cells you want to balance with this balancing circuitry. Okay, TP8485E, it has peak written on it. This is a 3 volt to 5.5 volt powered transceiver that meets RS485 and RS422 standards, and that's fairly near the output. Which one is which? UART and Bluetooth sits on the left there, and RS485 sits over on that side. Just one more chip to identify. Oh, there's this one over here, of course. Now this one is a BM8563 CMOS real-time clock and calendar. What on earth's it got a real-time clock and calendar? Interesting. And yeah, there is a little crystal there sitting next to it, which I presume provides the 32 kilohertz reference. What's this thing down here? I'm guessing some sort of buck or boost converter. Okay, this is possibly a MOSFET down here, and there is one more device on the back, and that is possibly, I haven't done a thorough check, a MOSFET gate driver. But I mean, there is a mass of exotic, I would say, circuitry on this device. It's quite surprising. Oh, and just one more thing, there are a couple of LEDs on here. One there, which is right underneath this little cutout here, this plastic window, which flashes quite brightly to show when this is balancing. And there's another one, or where was it? Here, which I think is just an on LED, and it doesn't really show through anyway. You can see it through this port, but you have to look at an angle, and it's quite dim, but it does appear to be on all the time. Now I'm just wondering whether the circuitry in here is circuitry that would be part of a BMS, because when you run up the app for this, it has all sorts of BMS settings which are irrelevant for this. Things like charge and discharge MOSFETs. Well, there are no charge and discharge MOSFETs in here because there are no high current paths into and out of a battery. But this is just the smart active balance part of that. So I wonder whether this circuitry has been copied over from a very complex BMS which has built-in active balancing. Right, let's plug in the UART cable. I've got to be a bit careful with this because, oh no, it goes in quite easily. But these wires are terribly thin, which is why I didn't want to pull it out by the wires. Okay, let's power it up. I'll connect it to my sodium-ion battery and we can see the app. Now, I originally put the app on my tablet here with all my other sort of Bluetooth and device apps. I also loaded in Smart BMS. So the app is called Balance BMS. It's on the Play Store. There's also Smart BMS, which is the DALI or daily version of the app. It's very, very similar, but it's all red. I don't know why the icon is green. That's rather strange. But 100 Balance have obviously gone for this blue corporate colouring. And although it runs on my tablet, for some reason, and this kept me guessing for many hours, it just doesn't see the Bluetooth anymore, and I don't quite know why. And it appears that Bluetooth on this tablet might have just died halfway through testing these apps. I'll have a quick look at the other app, actually. Let's run that one up, and yeah, you see it's all red, which is the colours of daily or DALI, local monitoring. And although it looks very different, it is essentially the same. But again, it just can't see the Bluetooth. So I had to load the app on my phone and I'll look at it from my phone. So I renamed my Bluetooth dongle Julian 100 because I just felt like it. And what it does is it shows you the voltage of the maximum voltage cell, the highest voltage cell, the voltage of the lowest voltage cell, the voltage difference, and of course they're very, very close. But it also down here shows you the 4 cell voltages to 3 decimal places. And although I haven't tested the precise accuracy, it does look pretty good. And I presume courtesy of the A to D conversions in that ARM chip. But yeah, you get to see the highest cell, which is in red, the lowest cell, which is in blue. and the other two cells. And I have seen videos of people using this software with 16S BMS, and it just lists all of the cells in this little panel here. Right, well, the first thing I need to do is unbalance this pack. So I've connected my red wire onto a magnet just on cell 1. So I'm charging cell 1. I'm using 2 amps and 4 volts so that I don't overcharge that cell. Okay, let's switch that on. You can see one of the passive balancing LEDs is coming on. Oh, I don't know whether I'm interrupting the charging of that on the LiFePO 4 BMS, but that probably is for another video. So I will leave that for a bit to unbalance. Oh, that's actually fired up now because it's flashing its green light. So it means it's seen the imbalance in the 4 cells, cell 1 having gone high, and it started balancing. Okay, so the difference between the highest and lowest cells is now 44 millivolts, and that should increase. It is cell 1 which I'm charging, so that one will start pushing up, and we should see this difference parameter increase. Let's see if the next update shows it as having increased. Yeah, 46 millivolts. Now you can see here state of charge, so this has got Coulomb counting, it's also got current, and you've got things like charge MOSFET is off, the discharge MOSFET is off. But I mean, all of this doesn't relate to active balancing. Yes, you've got the balancing is on, and you've got the balance current as 0.6 amps. Now I've got a feeling I set this to a lower balance current. You go into parameter setting, and oh, there's a lot of stuff in here, but I think it's in control center. Balancing is on, but yes, I've set the balance current to 0.8 amps. Now you can have a maximum of 1 amp, so let's set that. Then we've got to enter a password, 1 2 3 4 5 6, and it will update, and hopefully it will set the balancing current to 1 amp. Well, it doesn't appear to have taken that, but if we go back to the status display, balance current is 0.7 amps. No, it didn't take that. I have to say the software on this is, well, it's largely good, but every now and again it does strange things and misbehaves. Let's try setting that 1 amp again. Right, it's got it this time. So for some reason it didn't take it. This voltage is the voltage. Now I think all cells have to reach this voltage before it triggers balancing, which is really strange. You'd think that if one cell were above your threshold voltage, it would start balancing, but no, they all have to be above it. So you probably have to set that a bit lower than you might expect. And this is, it won't balance unless there's more than 20 millivolts of difference between 2 cells. So if we go back to here, it is balancing, which you can see from the flashing green light, because there's 50 millivolts of difference between the highest and the lowest cells. Now there's all sorts of temperature readings. I seem to remember that the MOS temperature did show, and it kind of showed the temperature inside this box, but for some reason that stopped functioning. I don't entirely know why. And there are some really weird anomalies. It shows the balance current currently as minus 0.8 amps, and this seems to go in tenths of an amp, so 100 milliamp increments or decrements. But when it shows minus 0.9 amps, it does something really bizarre. I'll try and capture it on camera. Yeah, there it is. It's minus 0.900000004. So there's some sort of bizarre calculation, rounding error when it shows 0.9 amps. 0.7 and 0.8 are fine, but 0.9 has this very strange 0.00004 on the end. Charge and discharge cycles irrelevant, because that would only be if we were driving a BMS and a Coulomb counter that could detect that you fully charged it and fully discharged it. And powering kilowatts, no, completely irrelevant to balancing. Now there are a mass of settings. I'll go through some of them. One interesting thing is that you can turn the balancing off with the balance switch. The charge switch and discharge switch, again, are related to BMSs, so that's irrelevant. But yes, you can turn the balancing off, and therefore you can use this not as a balancer. You can use it just simply to see the voltage of the 4 cells, which could be quite useful. Okay, parameter protections. So we've got, this is mostly for BMS, I think, the upper voltage protect, the low voltage protect, the charge over current protect, completely irrelevant for this unit, discharge over current protect. So none of those are relevant for the active balancer. Cell type, which you can set, it's currently lithium ion, you can set LFP, and it completely ignores you and stays on lithium ion. You can set the rated capacity of your pack, irrelevant for this application. Cell reference voltage, irrelevant. Waiting time, state of charge, apparently you can set it, but actually you can't, because it doesn't matter what you enter, it ignores you. Don't mess with the board 1 cell number, because if you change it from 4 on this 4S balancer, it then doesn't work. You've also got board 2 number of cells and board 3 number of cells. I have no idea what these things are. Irrelevant to the smart active balancer. Control center is the balance current, the threshold, and the delta things. We've seen all of that. Temperature protections, there's a whole series of 70 degree, minus 40 degrees, 70 degree, minus 40 degrees. I don't think any of these do anything. This one here, temp collect quantity, you can change that and it does weird things, but it's not really relevant. And parameter set, yes, you can change the name of your BMS. You can change the protocol type, actually. And there's a whole series of protocols. None, Pylon, GrowWatt, SOFAR, Voltronic Power, and GoodWe. You probably recognize some of those names. I don't. What are they, inverters or something like that? BMS software upgrade, I don't know whether that actually works. I don't see how it would. I think if you do that, it says enter some sort of file and it tells you the firmware version, and you can do a factory reset and you can reset that password of 123456. So masses of stuff in this app, a lot of which is completely irrelevant to the function of just active balancing. Right, we can now see that the delta, the difference between lowest and highest cells, is 70 something millivolts. Cell 1, which will be the highest one because that's the one I'm charging, is pushing up 3.47, and the other cells are at about 3.4. Yes, they are. Now, here's an interesting thing. Does this balancer balance as long as you've met the threshold, which is in another page, isn't it? It was 20 millivolts, the threshold where it actually engages balancing. Does it balance with this fixed current of 1 amp? This thing hovers around between 0.7, 0.8, 0.9. I don't think it's ever shown 1 amp. In other words, can it balance with 1 amp even if the difference between the voltages is very small? Now that behavior would be totally different. Gosh, it's getting dark in here. The sun's, well, there's no sun today. That's the problem this time of year. There's so little light and it lasts for so little time that it's very difficult to film. This one, like I say, if the cell voltages are quite far apart, it balances at a high current, and then that drops off like a exponential decay, so that when the cell voltages are very similar, the current that this little unit balances at is quite tiny. But does this device balance at this high current even if the cell voltages are quite close together? Yeah, I think it probably might, and looking at that circuitry, it certainly could. Okay, just to finish off then, let's see the actual effect of, I've got to remember where it is now, I think it's control center, turning off the balance switch. So let's turn that off and we should see that flashing light stop flashing, and it has. So it's responded to my turning off of balancing. So now this is not doing any balancing, it's really just acting as a cell voltage monitor, which, like I say, could make this thing quite useful even if it's not actually active balancing. Okay, probably quite a long video this one, but I did want to just impart everything that I've learnt about this smart active balancer and its corresponding not so smart just flying capacitor active balancer. and the differences between them, and a little bit about what's actually in this. And my goodness, is that complicated. And of course you've got the app which controls this and allows you to do all sorts of different things, but I'll leave it there. So cheerio.